So we work at GTRI. GTRI, the Georgia Tech Research Institute. It's the academic arm of Georgia Tech. So I feel like we're kind of in ACC land up here, so I can cherish our ACC tie. The GTRI is a reasonably large organization. We're on the order of about 1,400 engineers, about 2,000 staff, with a focus where we tend to be much more on the applied side of things, and with a big focus on DoD work. That's probably it is our primary customer, and a lot of our work is in the space of electronic warfare, which I'll talk about a little bit. We'll talk about kind of what our problem is that we're trying to solve, and then we can kind of dive into a little bit about what that means from a data standpoint. So, as I said, we are at GTRI, do a lot of work in electronic warfare, which is kind of our background. So for those that are not familiar, that's basically all the different technologies that come together to protect an airplane. Detecting radars, detecting missiles, jamming radars, shooting out, flares to try to confuse missiles, things like that. And our work specifically focuses on integrating things together. So a lot of times on a platform, you end up with these very specific solutions that have a niche use case, but there's nothing that brings it all together. And as air crews have gotten smaller, there's a need to try to bring that together. So we've been writing various products that have been on a lot of different older airplanes that try to integrate that together. And the main thing that's been a focus of ours over the last few years has been work in the correlation and fusion world. So if you look at that picture to the right, what you see is a whole lot of tracks on a display. Those little white symbols represent aircraft in the airspace. Now, one thing you may notice is that there are, for the most part, one symbol for an area of the airspace. In other words, you don't have a lot of overlapping symbols. Well, that's not an easy problem to solve. They are doing a lot of fusion under the hood to make that happen because they have lots of sensors that are seeing the same thing, and then they've got to say, okay, well, we believe this is the same thing. And obviously you have that in three-dimensional space, and there's a lot of factors that feed into that. So we write the algorithms that would make a display like that, although our display is not nearly as cool, that make a display like that, but that work on older airplanes that typically have much less awesome sensors and deal with a lot of other issues like latency and things that make the data quite nasty. So this is what we do, and I'm an electrical engineer by trade. So is Jimmy. Jimmy also moonlights as an ADA developer. For those that come out of the pure software world, you may have heard of ADA, and you can actually meet someone that still writes ADA, which is cool. And I've got the shout out to Ada Lovelace for those that know who she is. Our day job is to write software that goes on airplanes, but as part of that, we get a bunch of data back that we got to make sense out of. And so we've kind of found ourselves in a situation with a whole lot of data and trying to figure out smart ways to handle it. So at the most basic level, the aircraft lands, a bunch of binary data comes out, it goes into a big calculator, and then thumbs up everything worked. I mean, realistically, it's not exactly thumbs up everything worked. It's a little more questionable than that, but as we all know here, there's somebody in the loop. And so our goal is not to write the calculator that says that it worked. Our job is to put the tools in the hands of that guy so that he can decide what worked and what didn't work. And we tend to be on the side of the house, not on, there's a test organization that vets stuff, and that's separate from us. We typically are on did our stuff do what we wanted it to do? And if it didn't do what we wanted it to do, why did it not do what we wanted it to do? Which sometimes can be a really complicated question, and we need tools to help us figure that out. So a little context about data, and these numbers are very rough, but so I use the term sortie. So a sortie means a moment or an event where you have an aircraft take off and land. That's a sortie. So for every time that you have an aircraft in the sky, we call that a sortie. A mission is when you have a handful of aircraft that go fly together, and usually that's about 2 hours long. So they typically fly 2 to 4 ships, depending on the situation. We instrument and record all the data on the aircraft that are part of the test. That could be as little as 1, that could be as many as, let's say, 8. Sometimes it's bigger, but usually that's the maximum. There's a ton of aircraft that are in the airspace as well, other than the aircraft that are instrumented, which makes figuring out the right answer a little bit more complicated. But from a data perspective, we get these missions, and it's nominally about 20 gigabytes of data per sortie. A lot of that's video. We do not currently do anything with that video. It's all the cockpit displays and all these other things. We don't do anything with the video, but it's intertwined with the binary data. So we can't process the binary data without working our way through the video. So that big number matters. We nominally have about a terabyte of binary data, on the order of 6.5, 7 terabytes of total data, and a lot of intermediate data. And I'll talk a little bit about that. I mean, that's kind of a mess we found ourselves in as we start producing lots of stuff, and then you end up with these pieces along the way and trying to figure out how to best handle that. And I'll talk about that a little bit as we move through. So a little bit about the evolution. So you rewind back 10, 12 years ago, and at that time we were never worried about what happened across aircraft. It was always a single aircraft. So I'd have an aircraft data file, and I would do whatever it took to get the data into something that I could shove into Excel. And then, that back then, Excel was probably limited to, 64,000 rows. So we had way more data than that. So you had to do some decimation and things to get the data manageable. And you get Excel, and then it would be unbelievably painful. If you accidentally clicked on a cell, it would recalculate for 45 minutes, and you would cry for a little while. So needless to say, everyone today would say that Excel is an asinine tool for this, and I think we quickly agreed with that. So we ended up migrating and did a decent amount of work in Perl. The reason simply being that a lot of the developers had been using Perl for a long time, kind of as part of their build process and as part of their kind of working through getting all their software to do what they wanted to do. And so, honestly, there were Perl books laying around, and people started writing Perl. So it was kind of a Perl GNU stack, and I'll talk a little bit about what we did with GNU. And then we had that, and there's still people writing a lot of MATLAB. Everybody comes out of college writing MATLAB, and they think that's awesome. So, but it doesn't handle large data at all very well, and so plus it costs a lot of money, and that's sort of silly. So we said, okay, we need to get everybody off on these separate tangents and kind of focus. So we, I'd say probably 5 years ago, we made a decision to all kind of get within the PyData stack, and that has evolved. So we're now, everybody works inside that stack, but there's a lot of pieces that I'll kind of get into with that. And then that kind of last evolutionary piece, which is the hard part of trying to compare data across aircraft, and come with that. I imagine most everybody in here is familiar with this book. I just wanted to mention it from the standpoint that, it was kind of hilarious. We've been writing code and trying to make sense out of our data, and then we stumbled across this book, and it was like reading a book that was exactly written for our problem. And it was amazing. Jim and I were laughing about the fact that we'd written quite a bit of code that was probably not overly good and was completely unnecessary once we realized what pandas was. And we're like, wow, it interpolates all that for you. That's phenomenal. So it was great, and I would say, Wes McKinney's still an influence on you tend to pay attention to what he's doing, because a lot of the types of problems he's trying to solve are very much in line with the types of problems that we're trying to solve. So kind of at a basic level, here's our process. And we don't support just one aircraft, and we don't support one project. So this process is a little different depending on the aircraft and the project. But in general, we get a bunch of flight test data that we got to go decode, and it's a bunch of binary timestamp data, and you need some magical decoder ring, because it's hundreds and hundreds of messages that some vendor writes a document that tells you how to decode that data. That thing changes periodically, and that comes with its own headaches. There's also what I call this kind of mapper, because this sensor says that aircraft that number 29 means an F4 or whatever, and so you got to have all that. Usually that stuff's not machine readable, and so there's some work that has to be done there. And then you go kind of through this iterative, munging, wrangling, interpretation process. The storage thing is something that we have struggled with, and I'll talk a little bit about that, and kind of what our current solution is. And then obviously the whole point of it all, the analysis, and I'll talk about that a little bit as well. So I'll kind of hit those three main points. So, again, our data almost always comes to us in these things called IRIG Chapter 10, which doesn't need to mean anything to you except to say that it's a single large, 20 gigabyte file with everything that was recorded on that airplane all intertwined. It's pretty nastily how, I mean, obviously they're writing lots of stuff real time, so it's all intertwined, and it's a bit of a process to get it untangled. There's an open source C++ library that was written that we leverage to do that. We've basically written a Python wrapper around it that allows us to get the data. So that part is relatively easy to at least get it out of that iRig container. But then we got to go through this decodering process, and as I mentioned, that can be pretty intensive because there's a lot of messages, a lot of different ways things get formatted. One of the things that we did that was, I think, critical was making a machine readable version of that decoder ring. One of the things, we basically kind of extended an XML file to define how to read that binary string, and then so now you have hundreds to thousands of messages, and they each have an XML file telling you how to decode them. There's still some weaknesses there because there's places where a field way up here tells you how to interpret a field down here and things like that we haven't made that work as well as it needs to. We also found that can be relatively slow. We want to look at moving that to something else and also versioning it where we can know exactly when you decode something, what version of that decoder ring database you worked with. But one of the problems is the decoder ring is never machine readable. It's typically a Word file. Some of these things, hilariously, were written by some vendor 20 years ago, and the only thing anyone has is some scanned copy that you can barely read, and it's through trial and error that you actually figure out, oh, that was two's complement or whatever. So another problem that we have to work with is timestamp alignment. So still today, many of these aircraft struggle mightily with getting consistent timestamps throughout the airplane. So you'd think that it would simply take GPS time. All these aircraft do have GPS. I can take GPS time and I can disseminate. The problem is that you have a lot of different interfaces, a lot of old interfaces with latency. You got a lot of systems that reboot. When they reboot, they lose time and they don't necessarily get resynchronized. So there's just a lot of issues. So you end up having a bunch of different timestamps throughout the aircraft, and it's a process, to go figure out how to address that. Across airplanes, it's even harder. Again, ideally, everybody is on GPS time, and then it's easy, but it's never that easy because these aircraft have drift, a not insignificant amount of drift, and just other things. There's just people forget to set things or whatever. Now, I will say, time zone got mentioned earlier. One thing that's nice about this world is that everybody works in UTC. Nobody plays in time zones at all. We do get the issue that we do a lot of testing out west, and the rollover is like at 8 p.m., which it's not uncommon that we have tests that happen over rollover, and that's bitten us more times than we'd like to say. So another thing is coordinate frame alignment. So for those not familiar, there's a lot of different ways we can represent a point in space, and we typically think in lat long. We typically don't think in altitude because most of us are standing here on the ground. But in general, that's the way people talk about it. LLA, lat long altitude. That's one way to do it. Another way that's much better from a computation standpoint is to try to get things in ECEF XYZ, which is where the center of the Earth is 0, 0, 0, and I can represent anything in the world and obviously above the ground in XYZ, which is nice. And so, but not everybody reports that way. People report in different ways. There's also little nuances, like for those that aren't familiar, we all typically work in what's called the WGS 84 model of the world, and that pretends that we have this ellipse, and it's an ellipse that has certain things like flattening and things that we can find it, but it's still an ellipse. Well, the world isn't an ellipse. It's kind of a lumpy blob that is not exactly an ellipse, and there's places where the lumpiness is a little bigger and places where it's a little littler, and that's what we call the ellipsoid height difference, and it's basically databases that have that information, and it can go up and down 20, 30 feet. So there's things like that make it where are we really connecting things? So then you've got, that's how we represent things relative to the Earth. Then we've got the fact that we got to represent things relative to aircraft, and there's a lot of different ways to do that. And then sometimes the sensor will do it relative to them, the face of the sensor, not relative to the aircraft, so you got to deal with that. So there's a decent amount of work to kind of get all your coordinates aligned. As I mentioned, kind of another shout out to Pandas, and I wish I knew who did this artwork. I found it online one time and thought it was kind of awesome. Pandas does a whole lot of heavy lifting for us when it comes to munging and wrangling all the data. And again, I mean, nowadays that's kind of everything is within the data frame construct. So I'll get into this a little bit, but as for some of our big projects, we end up with this where we end up with this big pipeline where we would run it and it would go, translate a whole bunch of data and do a bunch of comparisons and do a bunch of, correlation analysis. We're figuring out what the right decision was as far as what aircraft were being associated. And it would take a very long time, does take a very long time. So we've looked at ways to improve it. And this is something we've started adopting, although I would say there's some experimentation to be done still. Numerical expressions is a library that has a couple of benefits, but basically the way it works is you put in as a string basically your math, and you can put all the math kind of in one string, and then numerical expressions goes and figures out the smartest way to execute that, kind of with vectorized data, so with numpys or data frames or whatever, and it's defaults to being a parallelized solution. It also takes advantage of Intel's MKL library, so there's a lot of goodness in that. We went and ran some data just to, and I think we kind of notionally done this, but actually to get it all in place was a little interesting in the preparations for this. So what the first line is telling you is simply I took 1,000,000 points where I went and created a list of 1,000,000 items where each one was a tuple with lat long and altitude. And then for the numpy it was three 1D arrays of a million latitude, 1,000,000 longitude, 1,000,000 altitude, and then pandas it was basically just a single data frame with those values. And then numba. So for those unfamiliar with numba is this idea that the only code is at GIT that you put at the top of your function, and what it does is it precompiles that function so that when you rerun that function, it's a precompiled version, meaning you're not having to go do the interpreter again. So it can theoretically be quite speedy. Also, we did a run with Cython. The Cython is where you're actually implementing C code inside of Python, and it can be a little hairy because you basically have to kind of build it through a C process, etc. But so what you see here is that we got up to 40% faster. Now, one of the things that I think is a little bit misleading about this data is, best I can tell, numerical expressions. I know numerical expressions is using all 4 cores appropriately. I do not think that's happening with anybody else. There's somewhat of an unfair 4K or 4x multiplier on the numerical expressions data. But if you look at some of these data, I mean, Cython, for example, which I'm pretty confident was not doing parallel function, 61 milliseconds for 1,000,000 points was quite good, compared to the 2 full seconds with native Python. But numerical expressions has been kind of what we've been leaning with, and it's quite easy to integrate, and it obviously works great with NumPy and Pandas. So all this is on GitHub, which is my SL Starnes GitHub. So storage. So this is a little bit of a I'd say where we're weakest and where we're most looking to change kind of how we do business. So originally, there's all these tools that had existed for a long time in the flight test data community, and in general, the flight test data community, which is quite large, has no concept of the scientific Python stack or anything like that. Like I think the Venn diagram overlap is exceptionally small. They have their own tools, quite a lot of them. And so there was a lot of tools that we leveraged that would take like aggregate data and turn it into CSVs. So we ended up with lots of CSVs, and that was kind of a starting point. And it was like, okay, read CSVs, do some computation. But then the problem is that along this process, we create a lot of data, right? So you say, okay, I need to know where this aircraft is. That's a message. Maybe that's a CSV. And then I need to know where the sensor's looking. For the purpose of that flight, that's a data file. And then I've got to compare that sensor to what I believe to be the truth value. So I have the position on the aircraft that I believed he was tracking. So now I need that, and then that's the comparison information, and then maybe I aggregate something, and that's something else. And what we ended up with is a ton of CSVs. Now CSVs has an inherent goodness in the fact that, anybody can open a CSV and it's valuable out of the gate, right? You can open Excel, you can plot with it, you can do things. And one of the things that we try to do is to have the data be accessible to the non-Pythonistas, and especially, if we're trying to get to the bottom of the problem, the software developers have to be integral to that, and they obviously could go and dig in the Python code, but that's not very efficient. So we want the products to be valuable, and so CSVs are good in that way. They're terrible in the sense that they're very inefficient from an I/O perspective. They have no way to track. They have no metadata of thing. We end up with these mile-long file names, which is sort of silly. So there's a lot of goodness in a solution that can do better than that. We've started doing a lot of stuff with HTF5. which is a lot faster. It actually supports metadata. We've, on some smaller projects, have started taking advantage of that. Haven't done that on our larger projects. But that's something I would say this is, again, kind of our weakest point, and I'll hit at the end kind of what we're looking at for next steps. So then we kind of come to this last piece of the analysis. And in my mind, I mean, this is the one I worry the least about, because if we get the other stuff right, how we store the data and how we kind of manage that process, then this can be, somebody can kind of come to the data with whatever solution they want from a visualization standpoint. But we've done a lot of different things. So I'll show up kind of our static plots and kind of talk about that in a second. But old school, we were doing this GNU plot stuff. Now everybody generally sticks with matplotlib, but it's always static because we can't. The only way matplotlib can be interactive is if you launch it out of Python. And imagine if we call a set time during the mission where like something was supposed to happen, like he's supposed to fly into this threat and do this maneuver. That we call a run. And so maybe during a test you'd have, let's say, 12 runs. And so I want to know on a certain day for a certain aircraft at a certain run, I want to see some information. Well, that would potentially create a set of static graphs. They can't create interactive graphs because I don't presuppose. Now, obviously, we could and should and have begun to build in smarter things like dashboards and things like that. But historically, that hasn't been how it's been. It's just been creating lots and lots of these graphs. We both have had great success and had problems with the kind of web-based solutions. There's a lot of goodness, and I kind of got a renewed interest to go reattack bokeh, which we've played with quite a bit, and for some of our smaller efforts have used. But the problem that we've always had is just the number of points. And while you can go through the process of kind of decimating the data, that has its problems. And needless to say, you can lose critical points. So we don't want to do that if we don't have to. Sarah was talking yesterday about the data shading piece to bokeh, which we have not played with extensively. But just in general, the JavaScript doesn't like when you throw it, a million points. So it's figuring out smart ways to handle that. PyQt-Graph is a 3D rendering engine that has kind of two things that we found very appealing. One is that it natively uses the GPU and has phenomenal performance with lots and lots of points, very good performance. And also, because it's got this kind of Qt base, it's all built in with the nice widget structure to go build, dashboards and things. I still think that we'd be much better off sticking inside of a Jupyter, web-based stack. And if we can find a way to do that and still deal with the massive amount of points that we have, I think that's where we'll end up. So, to us, as I mentioned before, the whole point to all this is kind of that accessibility, and so we want we want people to be able to kind of go ask questions to the data, and because we didn't end up creating a product that would have necessarily, you always end up in a situation where you're like, okay, here I am. It isn't necessarily where I would have wanted to be or expected to be, but here I am, and so where we are is where we have we found it easiest to go create a whole bunch of information that then somebody can go access as they need it, rather than having a method for somebody to query the information and return quick results. As I said, our day jobs, putting software on airplanes, the data thing is kind of something we fell into, and so it's always a trade-off between what you think you have time for, and when you end up down the road and you're like, wow, if 5 years ago we would have done this, we would have been much happier. But at the time you're like, we don't have time for that, so let's just write more Python and kind of keep building what we have, which has been somewhat of our struggle. We have the benefit of a new project that we're kicking off that's going to have, I think, a much larger amount of data, and it's all new data. So we have the benefit of kind of starting from scratch, which is part of what kind of generated a lot of our thinking on this topic of kind of how we got here and where we want to go. So two other things I want to mention on here, actually three other things. So one is Jinja. So I don't know if anyone's familiar with that. It's a templating engine, and D3, for anybody that's done D3, is immensely complicated. It's like, it's great, it's phenomenal, it looks awesome, but it's not trivial, and it's not to be taken lightly. But you can crib an awesome D3 and use Jinja, and like in 30 seconds you can take your pandas data and put it in some amazing D3 plot. So for crude, trying to make sense out of things, that has turned out to be a great tool. Cesium is a web-based graphics tool that is very geo-based, and they do a lot of work in kind of the outer space world, which isn't our world, but they have a lot of built-in things for visualizing in 3D that's been phenomenal. And again, for smaller data sets, it's been very good. And then the last thing is that human image recognition. I think this was mentioned by somebody earlier. Maybe it was Sarah's talk this morning. To us, it's a lot about putting the right information in the hands of the analyst or the engineer, such that they can figure out what's going on. We don't expect the software to figure out what's going on. I mean, that goes back to the beginning about this magical calculator that gives you the right answer. We know that isn't going to happen, so it's figuring out the right information such that people can look and they can see those nuanced differences or figure out, oh, this is why things are happening. And a lot of times it's about giving them many pieces of information at once. Ideally, things are integrated together where you're moving data and you're getting reactive displays, etc. So the static visualization piece. So this has kind of been this is the old school way we were doing things, producing bajillions of these files. And the one over on the right is basically it's showing you this would be for where we're taking a report of where a sensor thinks something is versus where it really is, and we're saying how much latitudinal error and longitudinal error and altitude error, and that's a phenomenal plot to have if on run 12 of this day I need to go look at that. Well, that plot's there and I can go look at it. But if I don't necessarily know what's wrong and I have 100,000 of these plots, then what do I do, right? That doesn't mean zero good. So that's kind of what we've been struggling with a little bit. Again, what I'd love is to have that, but that's interactive, and then I can, and that kind of gets that whole dashboard thing, which we've been trying to figure out the right solution for us. Here's another plot. So one of the things that we began to do is we gathered all this data. We have 300 flights, is to aggregate a lot of information, and we actually were able to find things that the program office for the aircraft, the prime, the vendors weren't aware of. So here's an example. Here's a sensor that ideally, with lots and lots of data points, and I don't know how many data points it is, but it's going to be at least in the 50,000, I would guess. This is you would expect if you had no bias in your system, that graph on the right would be dead in the crosshairs. So what you see is that there's bias. Imagine a sensor looking out into space from an aircraft. What you're seeing is bias, basically looking up and a little bit to the left. And so you can see, elevation angle is the angle, kind of coming off of the nose. Azimuth angle is going this way, and so you can see, the azimuth angle is kind of centered. The error is, and the elevation angle is a little over. And then again, in 3D. Now, so this is an example of the goodness that we had when we went and basically were able to aggregate tons and tons of information. Which our current process is to go cull through lots of intermediate data to then create other data, and it becomes part of kind of this pipeline. So this is actually the project that created that, and again, this is kind of an example of a project, but it happened to be one of our larger projects where we ended up creating this pipeline basically through makefiles, which I don't know if people are familiar with makefiles, but they are a way that usually people in the software building world will kind of handle dependencies and things like that, and so that's kind of how we used it here. The problem is and was that the pipeline is non-trivial for somebody to kind of walk up and interact with, except for the handful of people that kind of do the care and feeding of it, which is why we really want to move these kinds of things to a much more robust solution, something like Airflow or Luigi or something like that, and I'll talk a little bit about that at the end. As I said, the philosophy had been, rather than trying to solve some of the hard problems about resiliency, pedigree of the data. In other words, okay, I found a bug in this script. Well, what does that mean as far as all of my myriad amount of intermediate data? Do I go figure out what the ramifications of that were, or do I just delete everything and rerun it, which is typically easier, even though it takes 2 to 3 days. So that's kind of been the philosophy, which is again, you can see how you could do that from it makes sense at the moment to just rerun it, but in the grand scheme, it's unacceptably long-winded. So that's something else we're trying to figure out, is smart ways to kind of manage some of those pedigree issues. And then the goal is to have an engineer that isn't necessarily, somebody that knows Python but isn't intimately familiar with all of the pieces of this process, to be able to walk up and ask questions to the data. So a recent project we were doing, there's a rule out there that the FAA has for flying in the U.S. Called RVSM now I can't even remember what the R stands for, but vertical separation minimum, and it's basically, it has to do with how we stack our airplanes. So we used to stack them, this far apart. Now we stack them this far apart. In order to do that, everybody had to have goodness on their 3D solution in how they calculated their own position and how they monitored the goodness of that position. Well, the FAA mandated that a few years ago. A lot of military aircraft don't comply, which means they can't fly in the good airspace. They have to fly in the crappy airspace, which is either too low or too high, a lot less efficient, a lot less good for fuel, et cetera. So we were trying to do compliance, basically help them with compliance. We said, we have this huge data set. We want to ask a simple question. Tell me how, give me every time when I had an aircraft that flew straight and level for 2 minutes. Hilariously, we found very few occurrences of this, but the data, that we were able to ask that question and we were able to leverage this intermediate result, but it was not as easy as you would like it to be. And the ability for somebody to walk up and ask questions is definitely a work in progress. So to kind of highlight some of these hurdles, so that last one, making it easy to jump on the train. That is not my train, nor is that my metadata Metallica sticker. The resiliency of the pipeline. So managing, keeping that, that blast radius low, making sure that as things break, that it doesn't make basically cause all sorts of issues across the board, which has, been a bit of a problem, and I think why we're looking to migrate to a more of a managed pipeline solution. And then the pedigree issue. So this is, again, smart ways to manage how your data is good when things change upstream. And again, we don't have a good solution for that right now. And so metadata is a weak problem or is a problem in the flight test community. For the most part, metadata doesn't come with the data, and a lot of times the metadata that you might want to know is not even machine readable. It's a lot of times information you have to collect from people, what was on the airplane when it flew, what specific type model series airplane are we talking about, all those sorts of basic things isn't really collected. And so we've come up with a database of that metadata that we associate with all of our originating data, which is good. So that piece we solved. What we haven't solved is trying to iterate and kind of proliferate that information downstream, such that as you try to find your intermediate results, you can now ask those questions I was talking about earlier. I can know what type model series airplane I am. Right now we do that because we use the file names, which is an atrocious way to do it. So kind of in summary of what we are looking at as far as areas that kind of investigating is some sort of good workflow management. And I've got Dask up there kind of separate. I mean, I think Dask is a potential solution that would also be kind of this workflow management piece. But I don't know if people are familiar with Airflow, but Airflow and there's other tools like it. I mean, I mentioned 3 of them: Pinball, Luigi, and Airflow, and there's a myriad of other ones. But Airflow I have some familiarity with, and for us, it would give you not only the ability. It's basically you define your DAG. And then it goes and it decides how to run stuff. Right now we manually figure all that out through that make process and have to manage the dependencies manually. It does all that, but it gives you great visualization about what ran when, and then statistics on what took the longest, and then historical data on if things are taking longer than they should or whatever than they used to, and you can figure out as you make code changes what the impact is. So something like that I think makes a lot of sense for us. So I mentioned some of the computation pieces, and that's something that we're continuing to look at. I've got a coworker of mine that continues to say that if we did everything in Python, then life would be much better. I think he forgets that we'd have to write C, which we're trying not to do. So I got a few of these big data pieces down here, and I haven't really talked about that at all. But I'd say that, as I mentioned, we've kind of got this other program kicking off, and we've been trying to decide what that buys us and whether that makes sense. I mean, clearly we are not a big data product in this typical sense, and these tools come with a lot of baggage, from a maintenance standpoint. And for us, for every time that we're managing a Spark installation is the same guy that would otherwise be trying to make sense out of data. We don't have people that are on the operations side of the house. The other thing that makes our life kind of complicated is all of our analysis is air gapped, and so That's just painful in a myriad of ways, right? So first of all, you might say, hey, you want to do Spark? Go play Databricks. Go load your data in Databricks. Go play for a little while. We can't do that. We can't do anything. I mean, we did create a pretty good data set, unclassified data set, using this thing called ADSB, which is a soon-to-be mandated little transceiver that's going to go on every airplane bigger than, relatively small, and it's going to basically disseminate, and everybody basically beacons out their position constantly. There's some great websites that show the pictures of the Earth, and you see all the airplanes flying. Pretty cool. But there's feeds that you can download the data, and so we've done that, and that's a very nice data set. It's at least somewhat. We can have a lot of data that way. So we've been playing. We've actually got a cluster set up, and we've done some basic stuff. We got Dask up and running, so we've been trying to determine what the right answer there is, and whether it's worth it. I mentioned. We try to pay attention to what Wes McKinney's working on, and he's involved in IBIS. What kind of got us focused on IBIS? He's a Cloudera guy, so IBIS has got this tie to Impala. So if we were to do the kind of more SQL side of the big data solution, that seemed like a starting point. I don't know yet if that. First of all, we're not database people. For the most part, and we don't want to write SQL if we can help it. We're looking for what the right way to solve that is. I mentioned Dask. Dask is a kind of a scientific Python solution. I think we have a comfort with staying in that world, but again, trying to see if it's the right answer for us. Blaze is a little different. Blaze is basically a way to what's the word for when you make some. Anyway, I'll come back to it. And then the clustering thing. So typically think of this as predictive. Machine learning. You think of something that we want to create some predictive capability. For us, the clustering, we've been experimenting with trying to learn from the data through clustering. Trying to figure out which phenomenons are associated together. So I noticed that when the aircraft gets close to a ground threat, it typically gets terrible at figuring out where it is. Well, that's kind of an obvious one. The RF is just terrible at when you get close, your antenna patterns don't make any sense. But you could imagine that those sorts of things, the ones we don't know about, could be abstracted away. And that's the word I couldn't remember earlier. Blaze helps abstract your data. So that's something we're looking at as well. So I appreciate. I think we got a couple minutes left. I appreciate everyone's time and hearing about kind of our journey and our continued journey. And again, if people have thoughts on it, we'd certainly love to hear, and you can grab me or Jimmy at the bar later.
We do have a couple minutes for questions. Who's got the first question? Not Jimmy.
Hi, I'm with the Postal Service, and we're looking at a lot of telemetry data from vehicle tracking right now, and it's fairly impoverished, I guess, compared to your data. It's simple lat, longe, bearing speed, and XYZ accelerometer stuff. And one of the challenges we've been facing is to try to isolate events like backing up or making a U-turn to see if we can correlate those things with accident rates. Could you speak to how you've used, what methods you've used for isolating, turning the stream of telemetry into identifying a meaningful event out of it?
So I would say that is something that we've tried a lot of things, and we've had varying levels of success. I mean, what we found to be the most successful is putting the data in the hands of an analyst to go figure it out, which can't be the right answer in the big picture, because part of what we struggle with is it's a lot of data, and I can't have somebody look at all of it. But what we have run kind of trend finding software, mostly stuff that we baked ourselves, where I mentioned as part of this pipeline that it does a bunch of tasks, and one of those tasks is a completely separate process that's job is simply to go and find all sorts of error occurrences. And it's not just simply when a system says it's errored. There's lots of things that we've come to define as error occurrences, and we're able to graph those over time and can see where they align with things. I mean, as we try to make sense out of sensor data, typically, if a pilot is looking at his display and it doesn't do what he wants it to do, he typically blames the correlator because it didn't make a right decision. And our job is always to try to explain that that it's never our fault. It's always the sensor's fault, and so it's a lot of that kind of process of identifying where sensors are falling down. So I don't know. I mean, I can say we definitely had that problem and worked through it, but we don't have a good solution. I think part of what we'd like to do with some of this clustering work is to at least find relationships and where things happen. You talk about backing up in accident rates, things like that. The ability for me to basically run the data such that I can begin to see the relationships between things. I was very interested in the last talk about the graph theory and how they were able to find a bunch of types of relationships. I mean, that's a lot of times what we're trying to do when we have so much data with so much going on. So.
Hey, just I guess a comment and then a question. Just with my database hat on, I encourage your team to investigate maybe multiple solutions. Might really work well for you. Maybe you need like a time series data store, a high performance relational data store, and then a document store for tracking metadata or something. And so don't be afraid to branch out. And what might make that easier, and I guess is my question, is how are you managing this kind of growing stack of software? Is this something that everybody's got personally? Or I guess you mentioned the system is air-gapped, so I'm kind of curious how the system itself is managed.
I would almost say that managed is a strong word. So we are currently trying to get a Conda server basically on our side of the air gap. But right now we typically, all of the people are doing Python start with Anaconda. It's only when we really branch outside of what comes with the core Anaconda we have problems. Most of what we do, we have a couple of libraries, but we end up basically have a repository of tarballs and people go get stuff. Our team isn't very big. We do not currently share environments and things like that, which is something that I'd like to be able to do. But in a lot of ways, everybody is on their own, and we try to depend on YAML files and things like that for sharing data and making sure the requirements are well defined. But what ends up happening is we've grown just to have a lot of script software that again, it's like if you'd known where you were going, you would have probably taken a different road. But you end up where you are, and then you kind of have to move forward.
I'm going to cut off the questions now, and let's give another round of applause for Luke.
Thank you very much. I appreciate it.